Okay, this is an original question on universal gravitation in which a newly discovered planet in another solar system with a mass big M and radius big R and is assumed to have uniform density. And it's got two moons that move in circular orbits. Moon 1 has mass M1 and orbits at a distance R1. Moon 2 has a larger mass M2 and orbits at a greater distance R2 from the planet. So for part A, we want to just know, is it possible to determine which of the two moons experiences the greater magnitude of gravitational force from the planet using the information given? So the formula for universal gravitation is F sub G is equal to the universal gravitational constant, big G, times the mass of the two objects. In this case, for the two things we're comparing, one of the masses is the mass of the planet, so I'm just going to use big M, and then the other mass is the mass of each individual moon. So I'm just going to call that M without the little m, without the 1 or 2 subscript, and I'm going to divide that by the distance R for each moon from the planet, and I'm going to leave off the subscript again because in one case, it's going to be M1 and R1, and in the other case, it's going to be M2 and R2. And we just want to compare those two formulas. Well, if we look at the diagram, the larger moon, the moon with the larger mass, is farther away. So that means when this M is larger, this R is also larger. So it's actually not there's not a way to tell which one is going to exert more force on, or which one experiences greater force from the planet, because it all depends on how much bigger M is compared to the one of the M's is compared to the R. For example, let's say that Moon 2 of mass 2 is 4 times the mass of M1, but let's say the R2 is just twice the orbital radius of R1. If that was the case, you can see that the numerator increases by a factor of 4 when you're talking about Moon 2 compared to Moon 1, but the denominator also increases by a factor of 4 since that 2 would be squared. So with this combination of masses and radii, the force would be exactly the same on Moon 1 from the planet and on Moon 2 from the planet. So if the mass was a little bit high, if let's say the mass was a little bit higher, like 5, but the radius was the same, or if the radius was a little bit higher, but the mass was the same, then that could change which one of these experiences the greater force. So there's just simply no way to tell which one is going to get the greater force from the planet. So now let's just do some calculations. At the instant shown in the figure, the angular position of the two moons differs by 90 degrees. That means that if we just drew a straight line from here down to the moon, down to the planet, and from here over to the planet, this would be a 90-degree angle. So you can see that this forms a right triangle. And we know that the planet is going to experience a force from the Moon 2 going in that direction, and it's going to experience an attractive force from Moon 1 going in this direction. I'm basically just drawing like a giant free body diagram right directly on the figure for the planet. So in part 1 of part B, we want to find the magnitude of the net force exerted on the planet by the two moons. So that's just going to be the magnitude of this force going up. We're going to call this the gravitational force on the planet from Moon 2. And then we're going to have the gravitational force on the planet from Moon 1 down here. So I'm just calling them FGP2 and FGP1 for those individual gravitational forces. And because force is a vector, I can't just add them together. I have to add them together as vectors. And when they're at right angles to each other, you can add vectors using the Pythagorean theorem. And that would give the net force, which is going to point in, if I kind of turn this into a rectangle, it's going to point in that direction. And we can find the length of that force by doing the Pythagorean theorem on this force and this force. So if we go back down here, I'm going to say the gravitational force on the planet from moon 1 is equal to, and we're going to have the big G times the mass of the planet times the mass of moon 1, which was m1, divided by the orbital radius of moon 1 squared. And the gravitational force on the planet from moon 2 is going to be the same formula, but with the m1 replaced by an m2, and with the r1 replaced by an r2. And now we just need to do the vector sum of these two things using the Pythagorean theorem. So the total gravitational force, which is also going to be just the net force, which is the total gravitational force, is equal to the square root of FGP1 squared plus FGP2 squared. So I'm going to get those formulas plugged in. That's going to be the square root of big G, big M, little m1 over r1 squared plus big G, big M, m2 over r2 squared. And I've also got to square both of these things. That whole term is squared, and this whole term is squared. And if this were a free response question on the AP exam, it would be perfectly acceptable to leave the answer just like this, because this is a mathematically correct answer. However, if this was something like a multiple choice question, it is possible they might have the answers simplified down a little bit further. So it's a good idea to know how to simplify it. And in this case, the way to simplify this is you just take out some common terms. So we have a big G and a big M squared term in this first set of parentheses, and a big G, big M squared term in that second set of parentheses. So we can factor out a big G, big M squared, and then what's left is going to be m1 squared over r1 squared squared, which is r1 to the fourth. That's from the first term, and from the second term, we have an m2 squared over r2 to the fourth. And then this part right here would probably be taken outside of the square root sign, where it just becomes a big G, big M, and then all the rest of that stuff under the square root sign, all this stuff right here would basically be the same. All right, what is the magnitude of the force exerted by moon 1 on moon 2? So now we're just kind of ignoring the planet altogether. So let's forget that all this stuff over here even exists, and just focus on what's happening between moon 1 and moon 2. So for this one, we need to know what is that total distance from moon 1 to moon 2. And I guess we can go back and just put that triangle back on there, because we'll need that to get the distance. Since this distance here is r2 and this distance here is r1, we know that the total distance then from here to here, which I'm just going to call little r, is found with the Pythagorean theorem. So little r squared is equal to r1 squared plus r2 squared. We'll need that relationship in just a minute. So we can just say that the net force, or the gravitational force on moon 2 coming from moon 1 is equal to the universal gravitational constant times the two masses, which are m1 and m2, divided by the distance between those two masses, which we just called little r, squared. And then we just said that little r squared is equal to r1 squared plus r2 squared. So we can just replace that denominator with that, and we have the answer. So this is going to be big G, m1, m2 over r1 squared plus r2 squared. And that's it. All right, for parts C, D, and E, we want to determine if there is a configuration of the planet and moons that could result in a zero net force on several of the different things. So in part C, we want to see if we can get zero net force on Moon 1. So from where Moon 1 is located, since Moon 2 is on the outer orbit, it is possible when the planet and the moons are all lined up, that Moon 1 could be between Moon 2, which would be over here, and the planet. So in that configuration, it would look like Moon 2, and then Moon 1, the smaller moon, and then the planet. And as long as the gravitational force from the planet balances out the gravitational force from Moon 2, if those two forces are equal, then the net force would be zero. So what that means is that the gravitational force on Moon 1 caused by Moon 2, which is this arrow on the left, has to equal the gravitational force on Moon 1 caused by the planet. That's this arrow. As long as those two forces are equal, the net force would be zero. So let's just plug in some formulas. The gravitational force on Moon 1 from Moon 2 is equal to big G times Moon 1's mass times Moon 2's mass divided by the distance between Moon 1 and Moon 2 when they're lined up. Well, if we go back to the diagram, when the moons are lined up, if this distance right here from, let's say, from here to here is R1, and this distance, so that's your R1, and then the distance from here to here is R2, then the distance between those two moons would just be R2 minus R1. So we could go back down and say that in the denominator here, this is going to be R2 minus R1, that's the distance between the two moons, squared. This is going to be equal to the big G times Moon 1's mass, which is little m1, times the mass of the planet, big M, divided by the distance from Moon 1 to the planet, which is just R1 squared. And then it's just some simple canceling out we can do. We can say that this G and this G, the mass 1 and the mass 1's cancel out. And with what's left, that's a mathematical relationship. That's M2 over R2 minus R1 squared is equal to big M over R1 squared. It is possible if this were a multiple choice question, they might say like, they might give it to you as a ratio of masses, in which case maybe rearranging this to get something like M2 over big M. I'm bringing this big M down to the denominator here, and I'm going to bring this term up to the numerator over here. That's equal to R2 minus R1 squared over R1 squared. So, yes. Part D, is there a configuration of the planet and moons that could result in a net force on Moon 2? We're going back to this diagram again. Since Moon 2 is on the outer edge, no matter how the planets are lined up, Moon 2 can never end up between Moon 1 and the planet. So the two forces would always pull in either the same directions or kind of in where there's at least a component in the same direction. It's impossible for Moon 2 to end up between them, so it's impossible to have two forces in opposite directions. So for this one, we could just say no, and then mention the fact that you cannot get the Moon 2 between Moon 1 to have forces in opposite directions. And finally, is there a configuration of the planet and moons that could result in a zero net force on the planet? Well, we can do that if the planet ends up in the middle. So if we have the planet over here, we have Moon 1 where it is already located on the left side, and let's say that Moon 2, the larger moon, is on the right side. Then you have a gravitational force from Moon 2 pulling it to the right. You have a gravitational force from Moon 1 pulling it to the left. And as long as the gravitational force on the planet from Moon 1 is equal to the gravitational force on the planet from Moon 2, then it would work out. So let's plug the formulas in. This is going to be G times the mass of the planet, big M, times the mass of the moon, M1, divided by R1 squared. This is going to be equal to big G times the mass of the planet times mass 2 over R2 squared. And just as before, we have a big G and a big M that cancel out. And you've got the final answer as M1 over R1 squared is equal to M2 over R2 squared. Or it might be written, once again, as a ratio of masses, in which case it would be something like M1 over M2, bringing this term down here, and this term up here is equal to R1 squared over R2 squared.